This second video on gravitation, we're going to discuss satellite motion, the mechanical energy in an orbit, and Kepler's laws. So let's dive into satellite motion. Consider the Earth, radius r, and we have an extremely tall tower on Earth, which itself would likely sphericize from its own gravity. Nevertheless, it would accelerate into the Earth right through the crust. But we won't worry about those small details. We have our tower, and it's a lighthouse actually, but nevertheless somebody up here is going to launch a projectile straight off at a certain speed, and unfortunately it hits the Earth. And so you launch it a little faster, and it still hits the Earth. So these are too slow conditions for proper orbit. And just to confirm, if the Earth wasn't in the way, this trajectory would be an ellipse orbiting right around the center of mass, the center of gravity of the Earth, but the Earth gets in the way, otherwise it would actually produce an orbit. Well, at some point when you increase the speed, you arrive at that speed that's just right, and the projectile enters a circular orbit. In this case, we'll consider it a satellite. And so there's a gravitational force acting on the satellite toward the center of the Earth, producing an acceleration toward the center of the Earth, which of course is inward with respect to the circle. So it's a centripetal acceleration, also known as radial. So centripetal, radial, same thing. We know radial acceleration is v squared over r. So what produces that radial acceleration is Fg. And we say then that the Fg is, which is gmm over r squared, is the centripetal force to provide that radial acceleration. So sum of the forces is equal to the weight of this satellite. That is the only force acting on the satellite. Its weight, its mass times the g field it finds itself in, and that's ma sub c, so the centripetal force, and that is by definition mv squared over r. And we can cancel m's out, and with these two terms here, we solve for v orbit being rad rg. Now, look at mg is equal to mac again. mg is gmm over r squared. Mac, mv squared over r. Masses go away, the small masses. One of the r's goes away. And we have the velocity of orbit, orbital velocity. Or we could just say orbital speed, square root of gm, big G, big M, over the radius of the orbit.
Okay, we got this before.
Yes, the escape velocity, square root of 2gm over r. So we solved that earlier. And you'll notice the connection between these two, which we pointed out before. I mentioned how square root of gm over r is v orbit. And so we see that escape velocity is square root of 2 times the orbital velocity. Now let's go ahead and recognize that the speed is distance over time. Distance around the circle, 2 pi r over the period. So solve for period, and we have 2 pi r over v. So that's 2 pi r times 1 over v. So 1 over this is r over square root of r over gm. Now I'm going to stick this r back inside here because I don't like two r's to be sitting out there dangling. So we have orbital period, 2 pi square root of r cubed over gm. Let's now consider a bunch of physical quantities for a circular orbit with the following parameters. So we have a 1,000 kilogram satellite, we have the mass of the Earth, we have its radius. 300 kilometers is the orbital radius of the satellite. And let's figure out a lot of detail about this. You'll be expected to solve these kind of orbital mechanics problems as a routine. So, well, the orbital speed is root gm over r. The mechanical energy is k plus u, the kinetic plus the potential. Well, kinetic is 1/2 mv squared. We just solved for v. There's the orbit speed, so the square of that is gm over r. And now the gravitational potential energy, which we detailed in the previous video. So it's minus gmm over r. We're going to have to be very careful about this r, what r we're talking about. It's going to be the r from the center of the Earth out to its particular place of orbit. Well, this just evaluates the minus gmm over 2r. Very nice. That was very easy. Very good. Now let's find the speed, the period of the orbit, the radial acceleration, how much work it takes to put the satellite into orbit, and the work to escape from the Earth altogether once it's at this particular location. How much work do we have to do to make it escape forever and get out to infinity with zero motion but infinite distance? All right. So orbital speed, square root of gm over r, plug all the numbers in. The only thing to note here is this radius is the Earth's radius plus the additional 300 kilometers, 7730 meters per second. The period, 2 pi r over v, 2 pi total radius, adding these two numbers up, over the speed, 5430 seconds, which is equal to 90.5 minutes. That's kind of an interesting rule of thumb. You can assume something in orbit around the Earth takes, about an hour and a half. Granted, it depends on the radius, but this is pretty typical. About an hour and a half for an orbit around the Earth. Let's get the rest of the parameters. We have a radial, v squared over r, 7730 squared over r, 8.95 meters per second squared. Interesting. Notice that this does not deviate too far from the acceleration of gravity at the surface of the Earth. What this really is the acceleration of gravity 300 kilometers off the surface of the Earth. That is the radial acceleration. Same as the gravitational acceleration. All right, then we have work suborbit, which means the work to get that satellite into the orbit it finds itself in. Well, it's the difference in mechanical energy from position 2 to position 1. Now pay close attention to the details here of this solution. It's the mechanical energy where it is now compared to the mechanical energy to where it was. The final minus initial. The normal change you would think about. This is not the work done by gravity. Okay, this is work done by an external agent, namely the rocket engine itself, or engines. So it's an external agent doing positive work to take the spacecraft from position 1 to position 2. All right, so you have to shove it there, right? You have to thrust it there. So mechanical at 2 minus mechanical at 1. Well, the mechanical energy at 2 is already known. We just solved it, minus gmm over 2r. What's the mechanical energy at position 1? Well, it's the kinetic plus potential on the surface of the Earth. Position 1 is the surface of the Earth, so it's minus k1 plus u1. But what's k1? How fast is it moving on the launch pad ready to go? It's not. So this is equal to minus gmm over 2r minus negative gmm over r. R what? R sub e, the radius of the Earth. So that's the potential energy that it has sitting there on the launch pad. Well, we're almost done. GMM factors out 1 over RE minus 1 over 2R. And that gives us 3.26 times 10 to the 10 joules, which would be good for you to verify. So plug the numbers in and make sure that you're all good to go on that. Now, how much work is required to get this thing out to infinity? The beauty of our initial assessment of orbital mechanics and potential energy and how we define it is that we make the potential energy at infinity equal to 0. And so to get it out to infinity, the mechanical energy out there is, the total mechanical energy is 0, which means the kinetic and the potential are both 0. What a nice little help for us in problem solving. Thus, E2, the mechanical energy it has at position 2, which we already know, plus the additional work needed, is simply 0. Thus, the work required is negative E2. And that's negative E2, which is this value here, which we already know. 2.98 times 10 to the 10 joules. Notice it's a positive value because it takes positive work to get it out to infinity.